Hi, I'm Dave Dugan. I'm the president of EBTRON. Today we're going to be talking briefly about schools and school ventilation. As we're getting back into these classrooms, it's very important that the ventilation air is good so that we have a healthy environment for the students and the teachers. I think there's a lot of misinformation out there, so I want to do a real quick presentation on basically ventilation and IQ and things that we think you should be doing today. Let's just start off with who we are. If you don't know who we are, EBTRON's a manufacturer of electronic airflow measurement equipment. We started back in 1983, and we are located in Laura, South Carolina. And basically, we pioneered direct outdoor airflow measurement for monitoring control way back in 1989. And we have our technology is advanced thermal dispersion airflow measurement. When we talk about schools, one of the things that this is nothing new. We've had ventilation problems in schools. The EPA's identified it over the years. This is back from 2012. You know, most schools' ventilation rates are below recommended levels. However, ensuring adequate air ventilation rates in all classrooms can, and look at the number one thing they said there back in 2012, reduce absences and the transmission of infectious diseases. So how important is this today? And you can still go to the EPA and look at what they're saying, and they're still saying, hey, take action to improve indoor air quality in schools. And this was another thing that they mentioned just recently. Failure to respond promptly and effectively to poor indoor air quality in schools can lead to severe consequences. And again, isn't that true? When we look at ventilation in schools during COVID-19 and basically what the Centers for Disease Control recommends, you know, number one thing, increase outdoor air ventilation. I mean, it's still amazing to me how many people are doing what their people are trying to do. In fact, I've seen some people even reduce ventilation during this, which doesn't make any sense to me. And then disable demand control ventilation. Now, if you're not really familiar with how school ventilation systems work, basically the outdoor air is controlled, typically the CO2 levels in the space, in something that's called CO2 demand control ventilation. And it's really not about providing acceptable indoor air quality. It's really about saving energy, and that's what it's always been about. So, you know, fortunately, and you know, this sounds like a lot of money, but it really isn't that much money. There's recent federal funding has become available for schools. And basically, there's been a total of 81, close to $82 billion allocated. And it sounds like a lot until you look at the population. And it really isn't as much as you think. But we have the Governor's Emergency Education Relief Fund, which has put some money aside for non-public schools. And there's a list of things that this money can be used for. But one of them is improving ventilation systems to ensure healthy air in the non-public school. And we're hoping we can get people to realize this is where you need to spend your money. There's also the Elementary and Secondary School Emergency Relief Fund, which is public schools. It's $54.3 billion. And again, one of the things that's been approved is inspection, testing, maintenance, repair, replacement, and upgrade projects to improve the indoor air quality in school facilities, including mechanical and non-mechanical heating, ventilation, and air conditioning systems. So there is some money there. We just need to make sure that we use the money properly. And then there's a higher education emergency relief fund of $22.7 billion, but it's not as clear of whether or not those funds could be used for improving air quality. Now, to move on, a current document released in 2020 by ASHRAE is their positions document on infectious aerosols. And this is a very important document, very important to understand. So let's take a look at some of the highlights of this document. We start with what they consider to be the issue. And this is very important to anybody who's involved in buildings. Building science professionals, that's who we are, must recognize the importance of facility operations and ventilation systems in interrupting disease transmission. And they go on to say that dilution and extraction ventilation, so outdoor air, pressurization, airflow distribution and optimization, how the air actually is moving around the space, mechanical filtration, ultraviolet germicidal irradiation, and humidity control are effective strategies for reducing the risk of dissemination of infectious aerosols in buildings and transportation environments. So really, we're kind of being pointed, hey, we need to work on these HVAC systems, and particularly dilution ventilation or outdoor air. This is a little technical. I'll have my follow-up slide. The next slide's a little easier, but I like to put this in because I think that people need to understand what does airborne infectious disease mean, and how actually is it being disseminated. All right. So when you look at this, pathogen dissemination through the air occurs through droplets and aerosols, typically generated by coughing, sneezing, shouting, breathing, toilet flushing, some medical procedures, singing and talking, or pretty much everybody does in the classroom, right? And then it goes on to say that the majority of larger emitted droplets are drawn by gravity to land on surfaces within about 3 to 7 feet from the source. That's your 6-foot spacing. That's what drives the 6-foot spacing. And it says general dilution, ventilation, and pressure differentials do not significantly influence short-range transmission. So, our HVAC system, that really doesn't have a whole lot that it can deal with to help that. However, it goes on to say, conversely, dissemination of small infection aerosols include droplet nuclei from desiccation, which is drying, can be affected by airflow patterns in the space in general and airflow patterns surrounding the source in particular. Of special interest are small aerosols, okay, which can stay airborne and infectious for extended periods, several minutes, hours, or even days, and thus can travel longer distances and infect secondary hosts who have no contact with the primary host. This is really what the problem is in buildings, all right? While ventilation systems cannot interrupt the rapid settling of the large droplets, the ones that are going to be within that 6 foot, they can influence the transmission of droplet nuclei infectious aerosols. And that's what we need to be concerned about. So, for the less technical person, this is kind of a really good way to look at that. That person that you see there is infected. They talk, cough, whatever. There's a plume of air that comes from them. And then, there's basically some of the infectious particles are in that plume. And the larger particles are going to fall to the floor in that 3 to 7 foot range. However, some of these particles are going to desiccate. Now, they just could desiccate. Wintertime is when we get the most of our desiccation, right? Because the air is relatively dry. Even in moist climates, the relative humidity in spaces is low, okay? And it gets even worse when you're blowing hot, dry air. So I just kind of show that here to say, you have warm, dry air coming out, desiccate some of these particles, and now these particles can suspend for hours or even days. And once they get suspended, they can move throughout the room and throughout adjacent spaces, particularly if the systems are recirculating air. So that's where our problem is, okay? And if you take a look at this, I'm showing the COVID, basically infectious aerosols in the space. And if you don't have any outdoor air for dilution or any high-level mechanical filtration, meaning something that can actually have proven remove these, what's going to happen is that the infectious aerosols are going to just build, and they're going to become unsafe. And in fact, that's really what's happening in a lot of residences too. We hear about people getting sick in residences. Well, high occupant density residences, meaning, small houses with a lot of people in it. We have a big problem because all of our houses we don't have any real requirements for outdoor air in residential. And we also use very low level filters. So these particles just build up, okay? And it really creates a problem during COVID. So what ends up having to happen is some people will say to you, well, we just need to filter it. Well, filtering it isn't going to remove all of it, okay? It's still building in the space. Filtering is going to help. Okay, it's really, you need to do two things. You need to filter it and you need to bring in outdoor air to dilute it. And once you do that, if you bring in the proper dilution ventilation rates with the proper filtration, you can effectively, have a strategy that works on COVID. okay? And people come up with all different things right now, but honestly, this is the basics, okay? If you do the basics, you're going to improve the air quality. This is where we need to be spending our time and our money and improving these systems, all right? Okay, so what's going on? Well, when I take a look at this today, I look at indoor air quality in general. I mean, long before COVID, I was doing this, right? So I always looked at student well-being, and health and cognition or learning ability is really why you want to provide acceptable indoor air in buildings. Of course, with COVID, you also want to, reduce the airborne infectious disease. I also think that the school districts and the engineers have a lot of potential liability here. So there's a risk management side. And then there's a facility operation side and energy consumption. And when I look at energy consumption, it's kind of a conflict almost with student well-being, meaning we seem to really be in this mindset that what's important is to save energy, and we often lose sight of the fact that no, what's important is the student health and the teacher health and why we're sending these students to school in the first place, all right? And we seem to lose that on the energy side. And it's really, unfortunately, not standard 90.1, which is the energy standard that is used, is part of the problem. It drives these requirements for demand control ventilation in these higher occupant density classrooms. And personally, I think it's created some of our problems. And not everybody agrees with me on that, but I think there's plenty of evidence for it. One of the first ways it did it is by mandating demand control ventilation without really understanding the effect of the methods that are being allowed. And one of them is the use of CO2 sensing in the space. And a lot of people think that CO2 is all about, CO2 is an air quality measurement, or it's a contaminant and we need to keep the levels low. But really, that if you've been in this industry and know what's going on, what you recognize is that no, we've been measuring CO2 in this space because there's a relationship between CO2 and ventilation, and we can use that relationship to vary the outdoor air coming into the space as the population changes and reduce energy costs. That's really what we're doing. And if you take a look at if you really understand it, when you take a look at it, you find that what we care about is how much ventilation air or outdoor air we're bringing in. And we're measuring that in cubic feet per minute. And normally we're thinking in terms of cubic feet per minute of outdoor air per person. And so that if you look at the relationship between CO2 and ventilation, what you find is that the outdoor air CFM per person is proportional to the inverse of the CO2 level. And what that means basically is as the CO2 level drops, the outside air level associated with it increases. And there is truth to that. But the problem with it is there's a lot of assumptions that people have made, and they've always done this based on assuming that we're at steady state, meaning that the CO2 level has reached its plateau. And those things really don't necessarily happen. So one of the problems that we have that people don't seem to understand, I have read article after article now in the news that are clearly driven by people that do not understand what they're talking about when it comes down to CO2, okay? And one of the problems that we have is that we think that if the CO2 level is low, that we have adequate ventilation. Well, here's an example that I give all the time to people, and I'm like, hey, here I have these classrooms where I have an actual population of 10 people coming in, and 10 people are coming into each period, and I'm doing this CO2-based ventilation control. And so the blue dash line is 1,000 parts per million, which people think is below that is safe. Okay, and so I look at this and I say, well, you measured the CO2 level in the space, and it's well under 1,000 parts per million. Is this good or bad? And I say best or worst here because in my full-blown presentation, I have a series of these. I'm kind of quizzing people as I go along. So this is the last one. Best or worst? Is this best or worst? Most people look at this and say, well, look, the CO2 levels were well under 1,000 parts per million. The air quality is terrific. And then what I do is I show them, I say, well, hey, this is the CO2 level that you're looking at, you think you're great, yet the required ventilation for the ventilation standard is this green, and you provided the red dashed line, and actually you underventilated the classroom by 50%. And most people are like, what are you talking about? I was like, well, if you understood the relationship between CO2 and ventilation, you'd realize that when you walk into a space, the CO2 level in that space is pretty close to the ambient outdoors, and it's a big volume of space, and you have people producing CO2. And as they produce CO2, the CO2 level goes up, but until it gets to what your desired set point is, you're not necessarily bringing in any outdoor air. It's amazing to me how many people don't seem to understand that. So this is really not good indoor air quality. And so I can show you other examples too of uncertainties of CO2 measurement, but I don't have enough time in this presentation. I do have some really good presentations on it, quite a bit more technical than this one. Here's the other problem that I think we currently have that I don't think enough people are recognizing right now, because they just start referencing standards and codes and different things. Look, healthcare facilities have criteria for ventilation designs to mitigate airborne transmission of infectious diseases. I mean, we have standards for that because we expect there to be airborne infectious disease in healthcare. However, ASHRAE does not provide specific requirements for infectious disease control in homes, schools, prisons, shelters, transportation, or other public facilities because we didn't think this was going to be a problem, okay? And so but yet we're still building and designing to these standards and not understanding, hey, this does not address airborne infectious disease, all right? And so for those people that have an understanding of the ASHRAE standards, we have two standards. We have ventilation for acceptable indoor air quality, which is really what we go with in non-healthcare facilities, okay? It's ASHRAE Standard 62. And in healthcare facilities, we have a completely different set of standards here, and they're very different about how they require ventilation and very specific requirements for filtration. Okay, and I always tell people they should start to think about, if you're a professional in this business, you should start to look at the standard 170 ventilation of healthcare facilities, think about what we need to do during pandemics like COVID. All right, and I just, as just a simple example, without going through either one of the standards, that example I just showed you on the lag and the CO2 ventilation control. All right, basically, when we talk about something called air changes, and I'm talking about outdoor air changes. Basically, how many times is the volume of room replaced or displaced with outdoor air? Okay, and it's called outdoor air room changes. Okay, outdoor air changes. And basically, in that example I just showed you, we were under a half of an air change per hour. Yet, if you look at the requirements of the healthcare, Standard 170 usually runs in this 2 to 4 outdoor air changes, and during the COVID, the recommendations, even for like a patient room, has gone to 6 air changes. So we have an infected person in a patient room, and we're saying, hey, you know what, you need 6 air changes per hour, and it's just one person. We have a classroom of students, which my example there was 10 students, and we have 10 students in this classroom, and we're only providing a half air change per hour. There's something wrong there, okay? There's something wrong there. Now, the problem is the school systems were never designed to handle 6 air changes per hour. So you just can't say, well, we're going to go to 6 air changes per hour. That's not going to happen. But what you can do is you can say, let's go to design. And let's go to design and operate a design regardless of the population. Let's get away with this DCV. All right, that's what I'm saying. And I'm not the only one saying this. ASHRAE's position document on non-healthcare facilities, which is schools, basically the number one thing is increase outdoor air ventilation and then disable this demand controlled ventilation. But then they say open outdoor air dampers to 100% as indoor and outdoor conditions permit. It's a true statement, but too many people just think, well, I'll just open the outside air and bring it in. You can't do that in a lot of the country. You can't do it in the winter and the summer, and you just can't condition the air, so you've created some other problems, right? So it's not like as simple as some people would have you lead to believe. because you're going to have temperature control problems and humidity control problems. Okay, and they talk about temperature and humidity as well. That takes us kind of back to us, all right? Back in 1990, yes, that's 30 years ago, we published a paper in ASHRAE Journal that basically said the way that we're controlling or bringing in outdoor air into the space it isn't working. We need to measure it and we need to control it. And that's what happened here. And David Solberg is the primary author of this paper. And, myself, Dave Dugan, and Len Damiano, I always say we went along for the ride. This is Dave's paper. It was really a great paper, pointed out a lot of problems. But I still use this today because it's just such a slow-moving industry to get people to understand what they need to do. And what we basically demonstrate is that system effects, things like fan speed changes, and these dampers have issues that are that basically control for the outdoor air coming in, and even environmental factors like the wind on a building or temperature changes, which create something called stack pressure changes, really can result in your outdoor air set point being more than 50% off of what you think. And it ends up, if you know anything about this, if you're more than 50% off of what you want, then you're going to, and it could be significantly more, then you're going to have indoor air quality problems if you're on the short side, and you're going to have temperature control problems and humidity controls problems if you're on the high side. And that's what's going on in so many of our buildings and actually most of our schools. All right, so we have these problems. And so what we try to tell people is, look, you're spending money. You've got everybody telling you what to do, all right? But clearly, outside air, dilution ventilation is what you want to deal with. Everybody feels comfortable sitting outside, okay? And so we need to make sure that we bring in the maximum amount of outdoor air that we can during this pandemic, but without creating other problems such as temperature control problems and humidity control problems. So you want to measure the outdoor airflow rates. At a bare minimum, that's what you want to do. All right, and you may want to set alarms on that if the flow rates are below what your targets were. Okay, and then ultimately what you want to do is you actually want to control them. But not all of your systems are going to have the ability to do that short term. So you want to start by measuring, and then you want to go to control. And people can tell you anything they want to tell you about what you need to do. But the bottom line here is if you don't bring in the ventilation, that air that you need, the outdoor air that you need, you're going to have a problem. And if you bring in too much, more than the system can condition, you're also going to have a problem. So the only way you're going to get this right is to get it right. And the only way you're going to get it right is to measure it. All right? So when we look at this, we talk about, now this is a little more technical, so if you're a non-technical person taking a look at this, we basically want to operate and design for two operating modes, normal and pandemic mode. I mean, we never even thought about the word pandemic until over a year ago, right? But normal mode operation, we have offices and other low occupant density spaces. It's not about the CO2. It's about the ventilation air based on design conditions, because the office population doesn't change very much. And if you look at it, you'll find that the ventilation requirements don't change very much. So you measure and control the outdoor airflow rate to maintain what's required, okay, period, okay, during occupied periods, that's what you do. And when you get into these classrooms where now they're doing CO2 DCV almost all over, everywhere in the country, there's problems with it, okay? So when we get out of COVID, and I still think we need to do some serious improvement here, because it's clear that we've had ventilation problems in schools. It's well documented. It's not going away because we're not improving anything, okay? And there's different ways that we can go to do DCV. There's ways to improve it using CO2, and then there's even better ways to do it where you simply measure the number of people in the classroom. This pandemic mode, you simply switch over and just maintain the maximum. That's what you do. And it is that simple. Once you're measuring the airflow rates, you can do that. And I didn't mention this earlier, but a lot of these systems have something called an airside economizer, which a lot of folks are switching away from systems that have air side economizers. I think that they're missing out here. Air side economizers, when the outdoor air conditions are such that the air outdoors is more effective, less costly to cool than the return air from the space, you bring in as much of, you bring in outdoor air. In some cases, you bring in 100% outdoor air. I mean, that's fantastic. A lot of the systems that we're going to now don't have the ability to have air side economizers. But when you do have one, you have to make sure that you switch over properly, okay? There's a lot of problems with economizers. Okay, that's basically a real short version of this. So what you want to do, if you're an engineer or a professional that really wants to get into more detail, I have a series of presentations that are much more in depth, but they might take you, as much as 4 hours to get through all of them. But they're there and they're free for you, okay? If you have any specific questions, go ahead and reply to AskDave@engineeredsalescorp.com. All right, thanks very much for your time. All right, take care.